Hello, welcome back. So for this section, we'll talk about exponential models. Okay? Exponential growth function. Exponential growth is described by functions of the form yt is equal to y sub 0 e to the power of kt. The initial value of y at t is equal to 0 is y0. So y0 stands for the initial value, right? And the rate constant k, which is greater than 0, determine the rate of the growth. So k is what? The growth rate. So exponential growth is characterized by a constant relative growth rate. And sometimes we talk about doubling time, definition of doubling time. The quantity described by the function yt is equal to y0 e to the power of kt for k positive has a constant doubling time of t2, which is equal to ln of 2 divided by k with the same unit as t. So again, this is just coming from this formula. If you double y0, this would be 2 y0, and if you solve for t, you see t would be ln of 2 divided by k. So that's the doubling time. So let's go ahead and jump and solve this example. Human population growth rate vary geographically and fluctuate over time. The overall growth rate for world population peaked at an annual rate of 2.1% per year in the 1960s. Assume a world population of 6 billion in the 1999, which corresponds to t is equal to 0, and 7.4 billion in 2017, which is 18 years later. Find an exponential growth function for the world population that fits the two data points. And B, find the doubling time for the world population using the model in part A. And C, find absolute growth rate, which is y prime of t, and graph it for t 0 less than or equal to t and t is less than or equal to 50. According to the growth model, how fast is the population expected to be growing in 2021? Okay, let's go and start. So I'll say let yt be what? World population. Let yt be world population measured in billion, okay? Billions of people, t years, after which year 1999. So again, we know the function yt is given as y0 e to the power of kt, right? And where y0 and k must be determined. So if we read carefully, when t is equal to 0, the population was what? 6 billion, right? So in that case, we know y0 is equal to 6 billion. So which means we know yt would be equal to 6 e to the power of kt. But we also know 18 years later, the population grew to what? 7.4. So we know y of 18, which means we replace t by 18, 6e to the power of 18k. K18 is same thing as 18k, but 18k sound better. But at 18 years, what is the population? 7.4. So that's equal to 7.4. So we have to solve this one for k now. Solve for k. So of course, to solve this one for k, we have 6e to the power of 18k is equal to 7.4. We divide both sides by 6. So e to the power of 18k would be equal to 7.4 divided by 6, right? And then we apply ln on both sides because we want to get k by itself. You remember about the natural logarithm property. So 18k would be ln of 7.4 divided by 6. We are solving for k, so k would be ln of 7.4 divided by 6. Everything divided by 18, which would be, use your calculator. Which will be 0.01165. So therefore, k is this one, so yt will be 6e to the power of 0.01165t. So we just answer A, find the exponential growth function. So this is the exponential growth function. And then B, doubling time. The doubling time of the population is what? We have the formula T2 is equal to ln of 2 divided by k. So you don't need to, because the doubling time in when the population will be 12 billion. So we just could just replace yt in this right here by 12 billion and then solve. But since you have this formula, we have k, this answer will just be what? ln of 2 divided by 0.01165, which is approximately what? Use your calculator. 59.5 years. And then C, and then C, we are asked to find absolute growth rate y prime of t and graph it. So again, I'm going to graph, but you know how is the shape of exponential, right? So so growth rate y prime of t. So we know yt is given as 6 e to the power of 0.01165t. Then we will find y prime would be, find the derivative 6 times 0.01165 e to the power of 0.01165t, which means y prime of t will be 0.0699 e to the power of 0.0165t. And then now to sketch, I'm just going to give you a sketch. Don't mind. In this case, the initial value is what, 0.069. So let's set this is 0.05. Let's set this is 0.10, 0.15, and so on. So the graph will be something like this. This is the graph of y prime of t. Okay. This is the number of years, t, and this is billion of people per year. Billion of people per year. Okay. So D, the y-axis mean billion of people per year. So D, where according to the growth model, how fast is the population expected to be growing in the 2020? So in the 2020, that's t is equal to 21, right? So in 2020, t is equal to 21. So the growth rate is expected to be y prime of 21, which will be 0.0699 e to the power of 0.01165 times 21. And use your calculator. So this will give us approximately 0.0893 billion per year. Okay. Or if you want in a million, you can set what? Roughly 89 million per year. So this will be 0.083 billion per year, or approximately 89 million per year. Okay, let's move on to the next one. This is the APY of a saving account. Okay, that's a financial model. So the APY of a saving account is the percentage increase in balance over the course of a year. Suppose you deposit $500 in a saving account that has an APY of 6.18% per year. Assume the interest rate remain constant and no additional deposit or withdrawal are made. How long will it take the balance to reach 2,500. So again, this part as well is college algebra. So to solve this one, okay, so the solution. So I will still use the same formula. YT is equal to Y0 e to the power of KT, okay? So in this case, the initial saving deposit is what, 500. So that means my Y0 is 500, right? So we need to find again K, which is the growth rate. So we know our equation would be YT would be equal to 500 e to the power of KT. But again, the APY, which is 6.18% per year. So that is my K, right? Okay, sorry. Because if you read, they said, suppose you deposit 500 in a saving account that has an APY of 6.18% per year. So 1 year later, your Y0 will grow to what? 6.18%. So we know by saying that this means Y1 will always be equal to, it will increase, right? So which means you already have Y0. So it will be Y0 plus 6.18% of Y0. 6.18% is what? 0.0618 Y0 again. So if I combine this one, this means our Y1 will be equal to 1.0618 Y0, right? So basically, Y0 also is given, which is what? 500. So Y1 will be solving this one for K. Y1 will be basically 500 e to the power of K, right? Because my Y1 value we already know is 1.0618 times Y0. Does that make sense to you? Or let me, instead of putting again, instead of putting Y0, well, I mean 500, let me still put Y0 here, okay? Let me put Y0 because, and that should be equal to what? 1.0618 Y0. We divide both sides by Y0, so e to the power of K will be equal to 1.0618, right? So it's up to you. You can either change, even if I change my Y0 by 500, I would still have this one, okay? So K, because we are looking for K is not given. So applying ln on both sides, my K will be equal to ln of 1.0618, right? Which is what? Use your calculator, and that is 0.060. So now we have both Y0 and K. So we know K is 0.060. So my YT will be now 500 e to the power of 0.06 0t. So this is at any given time. So now I can go ahead and answer the question that is asked. How long will it take the balance to reach 2500? So now, since I have my function, then we are asked when yt will be equal to 2500. So we just need to solve 2500 is equal to 500 e to the power of 0.060, right? And then divide both sides by 500. So 5 would be equal to e to the power of 0.060. Then next, we apply ln. ln of 5 is equal to 0.060 t. We divide both sides by 0.060. So my t would be equal to ln of 5 divided by 0.060. So use your calculator again, which means t will be approximately what? 26.88. Then that's it. Okay. Next, we talk about energy. Among the many resources that people use, energy is certainly one of the most important. True, right? Assume the total energy used by a person, machine, or city is given by the function ET, because the power PT is the rate at which energy is used, where P T is equal to E prime of T. So you have to know there is a relationship between power and energy, right? Then the total amount of energy used between the time T is equal to A to the time T is equal to B is given. The total energy used is the integral of E prime of T dt, integral from A to B, or is also equal to the integral A to B pt dt. And we see that the energy is the area under the power curve. With this background, we can investigate a situation in which the rate of energy consumption increases exponentially. So let's do this example. At the beginning of 2010, the rate of energy consumption for the city of Denver was 7,000 megawatts MW, where 1 megawatt is equal to what? 10 to the power of 60 watts. That rate is expected to increase at an annual growth rate of 2% per year. A, find a function that gives the power or rate of energy consumption for all time after the beginning of 2010. B, find the total amount of energy used during 2018. C, find the function that gives the total cumulative amount of energy used by the city between 2010 and any time t greater than or equal to 0. Let's go and solve this one. Okay. So first thing I would say, rate as many times as possible to understand. At the beginning of 2010, the rate of energy consumption for the city of Denver was 7,000 megawatt, where that rate is expected to increase at an annual rate. So 2010, we will assume that let's TB greater than, so this is A first. Find the function, let me write A function that gives the power or rate of energy. Okay, so let T be positive first. Let T be greater than or equal to 0. B, the number of years. After 2010. And since we use PT as the power function, and let PT be the power function. And let PT be the power function that gives the rate of energy consumption. You don't need to write all of this, okay? That gives the rate of energy consumption, okay? Consumption at time t. So now, what the problem said? The problem said that rate is expected to increase at an annual growth rate of 2% per year. So that means what? Because P increase at a constant rate of 2% per year, it's just similar to the problem we just solved, okay? It increased exponentially. Therefore, look, what should I write? P increase at a constant rate. Of 2% per year. Because every year it's increased by 2%. So the population that is, I mean, the power increase 2% every year. So that is what it increased exponentially. So we can see that is it increases exponentially. Therefore, PT will be what? PT will be P0 e to the power of KT, where P0 is, in our case, P0 is what? Is given, right? In 2010, it was what? 7,000 megawatts. So P0 is 7,000. So now we need to find K, same thing, it increased by 2%. So that means P1 will be what? Again, P1 would be, don't forget again, P0 will be increased by what? 2% of P0. So plus 0.02 P0 again. P2 will be what? Again, so you see this total will be also increased by 2% and so on. So that's why we said P1 same type of problem. So we said P1, which will be equal to what? P0 e to the power of k will be what? If I add these two, it will give me what? 1.02 P0. And then we have to solve for k. We divide both sides by P0, so e to the power of k will be equal to 1.02. Then k will be ln of 1.02. Then use your calculator again. Give me the approximation. ln of 1.2 will give me 0.0198. Therefore, my PT would be what? 7,000 e to the power of 0.0198 t for t greater than or equal to 0. Okay, now B. We are asked to find the total amount of energy used during 2018. That's easy. So now B, because we have the power function. So B, 2018 correspond to what? Because this one is 2010. So that means between 8 to 9, right? 2018 corresponds to T has to be between 8 to 9, right? So then we will use the total energy used. Then we will write the total energy used would be equal to the integral 8 to 9 pt dt, which would be the integral from 8 to 9, 7,000 e to the power of 0.0198 t dt. So we know the rule of integration of exponential, right? So find the antiderivative of this one, which will give us 7,000 divided by 0.0198 e to the power of 0.0198 from 8 to 9. So again, I will not you substitute 9 for t. Sorry, I forgot to write t. You find the value, then you substitute the 8. So which will give us approximately 82, 83. because the unit of P are megawatt and T is measured in years, the unit of energy used are megawatt per year. So to convert megawatt, we multiply 8,000. We multiply by 8760 hour per year to get the total energy of about, because if you read okay, so or by being said, so megawatt year. Okay, so now next, mm, ask to find the function that gives the total cumulative amount of energy used by the city between 2010 and any time t. So we'll just replace C. So the total energy use between t is equal to 0 and any time or any future time t is, let's call it again, ET will be what? E0. E0 is what? The initial one, right? Plus the integral from 0 to t e prime of t dt, e prime of s. Let me use s because, or x, e prime of x dx. Or of course, e prime of x is same thing as p of x, or we can say this is same thing as e0 plus the integral from 0 to t p of x dx. Okay, so my et will be, but assume t is equal to 0 correspond to the beginning of 2010. We take E0 is what? Because at the beginning, when t is equal to 0, no energy was used. So that means E0 will be equal to 0. So substituting everything, so if we substitute everything, we'll get our ET will be equal to 0 plus the integral from 0 to t, 7,000 e to the power of 0.0198 x dx. And this integral will be 7,000 divided by 0.0198 e to the power of 0.0198 0 to t. So my function ET would be approximately 353,535 e to the power of 0.0198 t minus 1. Because if you substitute 0, this term would be 1, right? X is right here. I always forgot about that X. Okay. So let's go to the decay function, which is same thing as we will be doing same thing as growth function, but the difference is your k is negative in the decay. So exponential decay is described by a function of the form yt is equal to y0 e to the power of kt. The initial value of at t is equal to 0 is y of 0 is equal to y sub 0, and the rate of constant k is less than 0. Determine the determine the rate of decay. So exponential is characterized by a constant relative decay rate. Okay, the constant half-life is t half is equal to what? ln of 1/2 divided by k with the same unit as t. So that's for the exponential decay. So let's solve this example. Researchers determined that a fossilized bone has 30% of the C14 of a live bone. Estimate the age of the bone. Assume a half-life for C14 of 5,730 years. So the exponential decay function is what? Yt is equal to y sub 0 e to the power of kt, right? Represents, this one represents what? The amount of C14, the amount of C14 in bone T years. T years after the animal died, right? Okay, so now by the half-life formula, which is by the half-life formula, we know T of half-life is what? ln of 1/2 divided by k, right? We can see k would be equal to what? ln of 1/2 divided by T of 1/2, which would be ln of 1/2 divided by 5,730. So from there, we can see our k is approximately what? Use your calculator. You know, we are talking about decay, so you need to know your k has to give you a negative number, which is negative 0.000121. Right? So now we can write our function. So now if you said assume the amount of C14 in a living bone is Y0 over T, the amount of C14 in the fossilized bone decay to what, 30% of its initial value of, right? Or it's decreased by what, 0.03. So if that is, so of course, that means Y of T is equal to what? 30% of Y0. You know, 30% is what? 0.3 of Y0, right? So, which means 0.3 Y0 would be equal to what? Y0E. We have found K, negative 0.00121T. And then we solve this one for T. We divide both sides by Y0, so 0.3 will be equal to e to the power of negative 0.00121T. We apply ln, so ln of 0.03 will be equal to negative 0.00021T. Then we divide both sides by negative 0.0001T. So T will be equal to ln of 0.3 divided by negative 0.000121, which is approximately 9,950 years. So that's it for this section. See you in the next one.